Hello guys, after completing the chapter that is zeroth law of thermodynamics, which is the first law which we have to study in thermodynamics is zeroth law of thermodynamics. Now we are moving towards our next chapter, that is the energy interactions. Energy, as we know, there are two types of energy in the thermodynamics. One is your heat, one is your work. So how heat and work in different processes are transferring from system to surrounding or from surrounding to system, we have to study in this chapter that how the heat and work, that is the energy, how they are interacting with the system and surrounding. Right. First of all, we'll start with the work. What is a work? In thermodynamics, thermodynamic work is said to be done by the system if the sole effect on the things external to the system can be equated to raising of weights. I am again repeating that in thermodynamics, work is said to be done by the system. I am highlighting the important points, by the system. That system is doing work on the surrounding. By the system means system is doing work on the surrounding. By the system, if the sole effect means if the net effect of that work which is system is doing on the surrounding, the net effect on the things external to the system. This is important point, that is, it is external to the system. As we studied in our earlier chapter, that is the basics of thermodynamics, that there are two things, one is system, one is surrounding. Right? The part on which, or the reason on which our study is concerned about is known as system, and other than that system there is surrounding, and system and surrounding can be interacted with the help of this boundary. So boundary is differentiating between system and surrounding. So external to the system means the net sole effect of this work which done by the system on the surrounding can be equated of raising of weights. Means we can just take this, that the net effect can be equated to raising of weights. Some weight may be rise or some weight may fall down. Right? Lowering or raising of weights is the one and the same thing. Right? So the work which is external to the system, it can be equated to raising of weights. Weights may or may not be raising. Right? In that thermodynamics, if we are going towards any process, if there is a work transfer takes place, so we can imagine that this work which system is doing on the surrounding can either raise the weights or lower the weight, may or may not be happening actually with that process. Right? So we can just equate it to raising of weights, that weights may or may not rise, but effect can be seen. We can see the effect. Yes, it is capable of raising the weights or lowering the weights. Right? So this is the definition of thermodynamics work, that a work is said to be done by the system on surrounding, on external to the system, that is surrounding, if the net effect on the surrounding can be imagined or can be seen by some lowering or raising of weights, that weights may or may not rise. So this is the thermodynamics work. So from this definition, one thing is very clear, that thermodynamic work is said to be done only when this work crosses the boundary. If system is doing, if I am saying that system is doing work on the surrounding, or the case may be reverse, the surrounding can be doing some work on the system. So this work transfer, we are saying that work is transferred from system to surrounding, or work is transferred from surrounding to system only when it crosses the boundary. If the work is not crossing the boundary, then we are saying that there is no work done in the system. So the work must cross the boundary. Boundary must be crossed by this work. Then only we can say that the system is doing some work or surrounding is doing some work. If I am saying, if let us suppose this is our system, and external to the system is our surrounding, and system and surrounding are interacted with the help of this boundary. This is the boundary. So I am saying if system is doing some work on the surrounding, so I am saying this is the work which system is doing on the surrounding, and this is the work which surrounding is doing on the system. This is the work done on the system, this is the work done by the system. So that these two works can cross the boundary. This boundary must be crossed by these work, otherwise we are saying that there is no work done on the system or by the system. So there are two types of work. First one is work done by the system on the surrounding. Second one is work done on the system by the surrounding. So we have to make some sign conventions in thermodynamics. Sign conventions for thermodynamics is we are taking work done by the system on the surrounding as positive and work done on the system by the surrounding as negative. This is the standard sign conventions which we are taking in the thermodynamics. Work done by the system positive always, and work done on the system is negative. Right. Suppose we are taking this example. Suppose we have a battery. This is a battery. Through battery we are connecting with this motor, and with the help of this motor we are connecting one fan. When we on this battery, this motor will rotating, this motor will start rotating, and with the help of this motor this fan will start rotating. Suppose in this case I am saying that my system is this battery. We are saying that our system is that battery. So I am just draw a boundary, because to show the system we have to draw a boundary. So this is the system, battery is the system. So anything external to this battery is surrounding. Right. So we are saying that this system is producing this rotation of this motor, and because of the rotation of this motor this fan will start rotating. Right, this fan will start rotating. Now as per our definition of thermodynamic works, we are saying that we are considering that this system is doing some work on the surrounding if the net effect on the surrounding can be equated to raising of weights. In this example there are no weights here, that weights are not there which can be raised or which can be lowered. So that's why I am saying that weights may or may not be raised, but we can imagine, we can see, we can interpret by seeing the example. Yes, weight can be raised. If I connected a rope with this fan, suppose if I connected a rope here with this fan and I put some weight here, when the fan will start rotating, when this fan will start rotating just like a pulley, when this fan will start rotating, this weight will start lowering, this weight will start rising up, right? And if I rotate this fan in opposite direction, this weight will start lowering down, right? So now we can say that this battery is doing some work external to the system, and this weight can be rise or can be lower down. So the work is transferred between system and surrounding. Work is done by the system on the surrounding. So if I am saying that this is our system A, suppose this is our system A. So this system A is there, so work is transferred. Work is done by the system because the weight can be lowered. Work is done by the system because your weight is lowered or raised. Now I am just saying, if you said, no sir, we are taking this battery and this motor as a system. It is up to you, you can define system anywhere. It is up to you, you can choose any system. Now what we are saying, let us take this motor and battery as our system. Anything external to this is our surrounding. So this red dotted line is your boundary, and I am saying that suppose this is our system B. Suppose this is our system B. So if this battery and motor can be taken as a system, now the things external to this is fan, and fan is rotating because of motor, and the weights can be raised and can be lowered. So we can say that yes, in this case also work is transferred between system and surrounding. Work is done by the system on the surrounding because surrounding is fan is rotating, and this weight can be lowered or can be raised. So in this case also, if I am saying that this is your system B is also doing some work. Work is done by the system. In this case also, our work is done by the system. Now suppose if you are saying, no, we want to take all battery, motor and fan. We want to take all of them as a system. So okay, if I draw another boundary, suppose I am taking this motor, fan and battery, complete this as our system. Suppose this is our system. Now you are saying that no, we are taking this battery, motor and fan as a system. So I am saying, let us say this is our system C. This is our system C. Now the anything external to this system is our boundary. Now if we want to see that this battery is rotating this motor is rotating this fan will be connected with the help of a weight. This weight can be lowered or can be raised. But all this thing, that lowering of weight or raising of weight can be seen or is doing within the system. Within the system, these weights are lowering and weights can be raised. But there is no work transfer across the boundary. There is no work transfer from the system to the surrounding. We are not concerned if we are saying we want to find the work transfer. We are not concerned what is happening inside the system. In this case, inside the system, this fan is rotating, this weight can be lowered, can be raised. Depends upon the direction of rotation of this fan. But all this process is going on within the system. There is no interaction between system and surrounding, because now the fan is also in your system. So now in this case, we are saying that if we take battery, motor and fan as our system C, so if this is a system C, then in system C there is no work transfer. There is no work transfer because this work is not crossing this boundary. This work is not crossing this boundary. So in thermodynamics, work is said to be transferred only when it crosses the boundary. Something happened external to the system, then only work can be done. So this is the basic definition of your work. What is the definition of thermodynamic works? Okay, after studying what is the meaning of thermodynamic work, now we are more interested to know what are the values, what are the that formula for the work done by the system on the surrounding or work done by the surrounding on the system. So as we know from our earlier lectures, there are two types of system. One is an open system, one is closed system. So we will study open system and closed system separately, one by one. Closed system means, as we all know, in closed system there is no mass transfer. Mass cannot be transferred from the system or from the surrounding, and only energy transfer can take place. In a closed system, heat transfer can take place or work transfer can take place, but there is no mass transfer. So we'll start with the closed system work. So our next topic is the generalized equation for a non-flow work. Non-flow work means that your gas or any fluid is not flowing. There is not a open system so that mass transfer is taking place. In closed system, that mass which is trapped inside the beaker or inside the jar is not flowing. So we are saying that it is a non-flow work or a closed system work. So let us start with this closed system work. Suppose I have this piston cylinder arrangement. This is a cylinder, this is a piston, and inside this cylinder there is some gas, some air is filled in this, and at this position, when the piston is here, at this position the pressure inside the cylinder is P. Let us say the pressure inside this cylinder is P, and A is the cross-sectional area of this piston. This cross-sectional area of piston is A, and now this pressure P is exerting some force on this piston, right? If pressure inside the cylinder is more than the pressure outside at this area of this piston, so there is a pressure difference, and because of this pressure difference, this pressure will apply some force on this piston. So this piston will start moving in this direction as far as there is a pressure difference between these sides, right? Now the piston is, this pressure is applying some force on it. As we know that pressure is equal to force per unit area. The force which is acting on this piston will be equal to pressure into area of the piston. At this point, force acting on this piston is your pressure into the area, cross-sectional area of this piston. Right. Now the piston will be moving in this direction. So we are taking that assumption that this piston is moving very, very slowly. Right. The pressure difference between this point and this point is very, very less. Suppose if I am saying if the pressure here is 1 bar, so the pressure here will be 0.9999 bar. Very less pressure difference is there, because we want that this piston is moving very slowly, so that we can track that, so that at each and every point the piston or the system must be in equilibrium. If suppose this piston is moving very fast, suppose the pressure difference will be like, if here is 10 bar, here is 1 bar, this piston will go from this point to this point as a very sudden. So when the piston is, suppose this is the piston stroke, this much is the piston stroke for 10 bar and 1 bar pressure difference. So the piston is going from this point to this point very fast within no time. So we are saying that at each and every point where the piston is, it is not in equilibrium position. We are not able to maintain that equilibrium position. So in order to maintain a equilibrium position at each and every point, so we want this piston will be moving in this direction very slowly. So the pressure difference between these 2 points will be, if here is 1 bar, there is 0.999 bar. It is a very slow process. If that is the case, if in a thermodynamics any process is a very slow process, so we can say that it is quasi-static. Right? There is a word name as your quasi-static process. Quasi-static. Static means at rest. Static, as we know, at rest. Quasi means it seems to be at rest. Right? If we are seeing this, the piston is moving very, very slow. So we are saying that, yeah, piston is just like a static body, just because it is very slow. You cannot differentiate between that. So this process will be a quasi-static process, because we want at each and every point when the piston is moving, at each and every point the system must be in equilibrium. Because if the system is in equilibrium, we want, so if this is the case, when the system is in equilibrium, that process is known as your reversible process. Right? We will study it later on, how reversible process must be in equilibrium, or how the reversible process must be in quasi-static process. Right? So this piston is moving here in this direction very slowly. Suppose I am taking that the piston is going from this point to this point. Suppose because of this P pressure, the piston is going from this point to this point, and let us say the distance traveled by the system is dx. We are taking a very small movement of a piston to analyze this work. So we are saying, suppose only very less distance traveled by the piston, let us say dx. So the work done by the system on the surrounding, this is the system, this cylinder is our system, this cylinder is our system. I am drawing the boundary here. This cylinder is our system, air inside this cylinder is our system. So if the piston is moving in this direction, so we can say that work is done by the system on the surrounding, because the piston is external to the system, so the work is going outside the system. So we are saying work is transferring. That is okay. Now I am saying work done by the system on the surrounding, if the piston is moving for small distance, that is dx, will be equal to, we know that work is equal to force into distance, force into displacement. So we are saying a small work done by the piston or done by the system on the surrounding when piston is moving from this point to this point will be equal to force which is equal to P into A, pressure into area, into distance traveled by the piston, that is dx. Right. This is a small work done by the system on the surrounding in this case. Now we want to know what is the total work done by the system. We want to know what is the total work done by the system when piston is moving from one top dead center to bottom dead center, or from one stroke we want to know the total work done by the piston from here to here. If the piston is traveled from this point to this point, what is the total work done by the system? So we know that if this is a work done for an infinite small displacement, and if we want to know what is the total work done, we have to integrate it. So we are saying that force into displacement is a total work, or is a work dW, and I write force is equal to pressure into area. Force is equal to pressure into area into dx, and area into distance, area into dx. This area of piston and displacement, this displacement is the volume swept by the piston. When the piston is moving from this point to this point, this much volume it sweep. This much volume it sweep in this direction. So I am writing this is the volume dV of this volume is dV. So dW is equal to P into dV. This is the work done by the system on the surrounding when piston is moving at a distance dx. Now we want to know what is the total work done by the piston when it is going from state, say let us say from point 1 to point 2, when it is going, how much total work done? So we are integrating this dW. So if I am saying that integration of dW is equal to integration of P into dV, is equal to integration of P into dV, and this, if this P is constant, so we are saying that this is equal to integration of P into dV. This pressure may be constant, may not be constant, right? So this is the work done. The formula for work done in case of your closed system is your W is equal to integration of P into dV, right? Now we are assuming two assumptions in this case. In thermodynamics, assumptions plays a very important role. Once you are deriving an equation, the assumption is very important. So assumptions of using that closed system work is equal to integration PdV is, first one is your closed system must be closed, there is no mass transfer, and second, I am taking here a reversible process, so the second one is your reversible process. So this work done, which is equal to PdV, is only applicable for closed system reversible process. If the process is irreversible, if this pressure difference is very high, the piston is moving from this point to this point suddenly, so we cannot say that the work in that case will be equal to integration PdV, because this formula is only valid for a reversible process. Now let us suppose if I am drawing this process on a PV diagram. I am drawing this process on a PV diagram. Suppose this is my point 1, which is at a pressure P1, volume is V1. Now when a piston is moving, this is the process, it is going to point 2, final point, that is your at pressure P2 and volume V2. Right, this is a PV diagram for this process. This may be any line, I am just drawing a curve. Right, we want to know what is the total work done by the system on the surrounding from this, for this process 1 to 2. We want to know what is the work done by the process, by the system in this process 1 to 2. So we are saying that work done will be is equal to integration of P into dV from point 1 to point 2. We set the limits from stage 1 to stage 2. As we know, the integration in this case will be the area under the curve. The integration will be the area under the curve. So if I projected this curve on the volume axis, if I take this curve on the volume axis, so the area under this curve, this area, this total area is equal to the closed system work, right? This area will be the closed system work in case of a closed system reversible process. This is a reversible process, that's why I show it as a firm line or a continuous line. If it is a irreversible process, we have to show it with a dotted line as we teach earlier, right? So this area under the curve, area under the PV diagram, when projected on the volume axis, will give us a closed system work. So this is the work done. This value will give you the work done by the system on the surrounding in closed system reversible process. Now we have to see what are the important points regarding our work transfer, right? First of all, we already seen in the definition of our thermodynamic work that work must cross the boundary. If the work is not crossing the boundary, if in this case, if I am taking this whole piston cylinder arrangement as my system, if I taking this complete as my system, there is no work transfer here because work is not crossing the boundary. So the thermodynamic work must cross the boundary. The first important point is it is a boundary phenomena. It will always cross the boundary. Second one is work is a path function. There are two types of function as we studied. One is point function. We studied in the properties when we are studying the properties of a thermodynamic properties. We are saying that properties are point functions. That properties are only dependent upon the initial and final state. Unless until there is a change in property, that state will remain constant. Right. So work is not a point function, work is a path function. Right. So we will see this, how the work is a path function. Suppose this is a PV diagram. Right. There is a one point, this is initial point 1, this is a final point 2. Right. We have to go from point 1 to point 2. This is a PV diagram, we have to go from point 1 to point 2. So there are n number of paths taken by the process to go from point 1 and point 2. We are taking two paths. Suppose one path is going along this process A. One path is going along this process A and another process is this B. This is the path of B and this is the path of A. As we know, we want to find what is the thermodynamic work done by different processes when the process is occurring between point 1 and point 2. Right. If I am projected these curves on the volume axis, if I am projecting these works on the volume axis, this is the projection. So the work done by the system on the surrounding, if when the process is A, is the area under the curve of process A. This area, this shaded area will give you the work done by the system for the process 1A2 if it is taking this path. Now we want to calculate what is the work done by the system on the surrounding if it is taking B process. Right. As we know, the work done will be the area under the curve. So the curve is this B. So the area under the curve will be this one. Area under the curve will be this one. So this red shaded area is your work done in the B process and this blue shaded area is your work done in the A process. So as we see from the diagram that both of the areas are not equal. Both of the areas are not equal. So we can say that work done by a process is depending upon the path taken by that process. As path changes, work transfer will change. So in this case, both the process A and B, initial and final points are same. Initial and final states are same, but paths are different, thereby work transfer will be different. And so we can say that if this is the case, initial and final points are same, but the value of work is different. So we can say that work is a path function, not a point function. Work is not depending upon the initial and final points. If work is a point function, then for the both of the case, work should be same because initial and final points for both of the process are same. So work is a path function, not a point function. So if work is not a point function, then work is not a property, because we know that properties like your temperature, pressure, these are the properties of a system. So properties are depending upon the points, initial and final points. They are not depending upon the path which that process followed. But here your work is following, work is not a point function, work is depending upon the path. So if work is depending upon a path, so it is not a property. And if it is not a property, then it will not be an exact differential. Work is not be an exact differential. Work is a inexact differential. So we are saying that the integration of dW from point 1 to 2 will not be equal to W2 minus W1. We have to integrate it. It is not an exact differential. So these are the four important points regarding work transfer. First one is it will always cross the boundary. Keep it in mind, it will always cross the boundary. If boundary is not crossed by the work, then work is 0. Or work is a path function, not a point function. It depends upon the path taken by the process. If it is a path function, it will not be a property. If it will not be a property, it will not be an exact differential. This is a important points regarding closed system work.